1 plus 1 should give us 2. On a different cell, one thing to note about the Jupyter Notebook application is that to see the result of an operation, you don't always have to print it. You can simply declare the Python operation like so, 1 plus 1, run it, and it should still show you what the output is. Except now, notice that when you print it, it doesn't show the out text. Whereas in this case, by removing the print statement, it does. What does that mean? Well, if we were running this code on some text editor, which is what we're going to do in the near future, to see the results of the output, let's say on the terminal or command prompt, we would have to print it. Simply declaring the operation won't tell us anything about the results. In the case of Jupyter Notebook, simply running the code inside of a cell without printing is enough to tell us about the output. Not a major point, but good to keep in mind. Another arithmetic operator is subtraction, which in Python is denoted by the usual minus sign. Therefore, 1 minus 1 should indeed give us an output of 0. Multiplication, as you've guessed it, it is denoted by the asterisk. Therefore, 7 times 7 would give us 49. And division in Python, as you've also guessed it, is denoted by the slash symbol. No tricks there. So 10 divided by 5 gives us 2. Another important thing to note is that Python follows the order of operation. For example, if I were to print 6 plus 9 times 3 plus 3, the output would be 36. Since as per the order of operation, multiplication must occur first. 9 times 3 gives 27. Then you add 3 and 6 to give 36. If you want to ensure addition occurs first, just like you would in everyday math, place brackets around 6 and 9, and brackets around 3 and 3. Adding 6 and 9 to make 15, adding 3 and 3 to make 6, multiplying 6 and 15 to give 90. This is just basic mathematic order of operation. But let's also talk about the modulus operator, denoted by the percent symbol. The modulus operator simply outputs the remainder of a division. For example, 6 modulus 2, if we run this, should give us 0, since dividing 6 by 2 gives a remainder of 0. 9 modulus 2 would give an output of 1, since 9 divided by 2 gives a remainder of 1. Now what about exponents? A common mistake is to use the caret symbol for exponents. In Python, this is incorrect and represents a bitwise operation. We'll look more into it later on. To denote exponents, we use a double asterisk, such that 6 double asterisk 2, 6 to the power of 2, if you run it, obviously 6 to the power of 2 gives 36. Finally, the last operator I want to talk about is the double slash, which divides but also rounds down to the nearest integer. So 13 divided by 2, as you know, is 6.5, but if you run this, it rounds down to 6. That's all for arithmetic operators. Nothing scary so far, just simple mathematical operations that are commonly done in Python. Inside of Jupyter Notebooks, we'll create a variable labeled age is equal to a value of 25. If you output this variable, this value, and run it, indeed it gives us 25. The equal sign is an assignment operator that assigns the value on the right to the name on the left. For the purpose of concision, Python also lets us assign multiple values to multiple variable names. For example, what you would do in another language is write age is equal to 25, name is equal to Jane, and gender is equal to female. With Python, you can use the comma operator to assign all 3 variables at once. That is, I can write age, name, and gender is equal to, make sure everything is in the proper order with respect to your variable names, such that age will be 25, name will be Jane, and gender female. Only use this notation with closely related variables. For example, all the variables here represent the characteristics of a person. You could also do this with dimensions like width and height, as they both represent the dimensions of some shape, most likely a rectangle. Try to keep your variable names as descriptive as possible, to ensure that you're always aware of what's going on in your code. For instance, you can never have any space in between. If I'm to assign blood type is equal to AB, I can't actually do that. If I try to run it, it should give me an error. In such a case, you would want to use an underscore to separate your two words, like so. Blood type is equal to AB, and this should run just fine. Also, only use letters and numbers in your variable names. Don't use symbols like $sign or modulus. As a convention, all variable names should be lowercase and have an underscore in between. Do not capitalize anything as you would in camel case. Always use the snake case, which connects all words with underscores. Finally, there are certain keywords in Python that you cannot use as variable names. They are reserved since they carry very specific purposes in Python. You'll learn more about them throughout the course, but words like return, while, or import are reserved words. You'll learn more about them as you progress through the crash course. One thing to also note about Pythonic variables is that you can assign them a new value. Storing a new value to a specific variable erases the old one. For example, let's assume that 5 years later, Jane is now 30. I can reassign this variable age from equaling 25 to age is equal to age plus 5. If I print this, it should give me 30. So we took its current age and added 5. Perfect. This also introduces the plus equal assignment operator. The plus equal assignment operator, you've probably seen in other languages, is a shorthand operator which lets us express the operation more cleanly, without having to write the name of the variable twice. Basically, what we did here was take the current value and increment by 5. Similarly, we can write age plus equal 5, which once again takes the current value of the age and adds 5, but does it more concisely. If I output the value of this, it indeed increments it by 5. There is a similar operator, the minus equal operator, which, as you guessed it, lets us decrement numbers. So instead of writing age is equal to age minus 5, let's assume for whatever reason Jane is getting younger by 5 years. Instead of writing this out, you can simply write age minus equals 5. And what that will do is decrement our age by 5 every time. What we'll do is actually go ahead and print out the result of the output, and we get 30. That is all for variables. Pretty easy stuff so far. It just takes a little practice to get used to, but the concept should be very straightforward. Name equal to Amir. Print the name and print the variable type. Print type name. If you run this cell, it gives us a string type str. If I replace Amir with double quotes Amir, it should work the exact same way. It outputs the same result and it's still a string. However, there are some cases where one is advantageous over the other. For example, what if I wanted double quotes inside of my string? How would I do it? Let's try this. Set dialog equal to Amir said, "Hello, John." To which John replied, "Hello, Amir." All we have is a string with some dialogue inside, the dialogue indicated by the double quotes. If I try to run this, I'll get an error. There are two solutions to this. Instead of writing the string with a double quote, use a single quote. And you should be good to go. That way, you can use double quotes inside of your string. Let's run this. And everything works out fine. Let's assume inside of that same string, I wanted to use single quotes as well. That is, instead of John saying, "Hello, Amir," he says, "You're the best." You're the best. This doesn't work. You can't have single quotes inside of a single quote string. Not like that, at least. Unless we use a backslash in our string to include this quote. You're the best, like so. Print it, and we're good to go. If you don't put the backslash, Python is going to think that this quote is what ends the string, and everything after it is extraneous. By putting the backslash, you're telling Python this quote is part of the string. It's not ending it. A common operation in strings is to concatenate them. We can concatenate strings. We can add strings the same way we added integers and floats with the plus operator. For example, set a variable segment1 is equal to I am 25, and set another variable segment2 is equal to years old. We need to concatenate these two strings to make a full sentence. What we'll do is we'll write full sentence is equal to segment1 plus segment2. If I print this full sentence, print full sentence, they are indeed concatenated, except we need a spacing in between them. So in between the two segments, we'll also add an empty space, plus empty space, and plus the segment number 2. And this achieves spacing in between the two strings. What's interesting is that strings can also be multiplied. For example, if I am a parrot and I want to repeat this sentence 10 times, simply print full sentence times 10. Output the result, and we get exactly what we expect. It repeats 10 times. Let's actually go ahead and set full sentence times 10 equal to a variable long sentence. Long sentence is equal to full sentence times 10. What if I asked you to count all the characters in that long sentence? That would take you a while. Well, I mean, you could just count the characters in this one sentence and multiply it by 10, but that's not very fun. Python has a useful built-in length function that returns the length of not only strings, but collection types as well. We can obtain the length of this long string by using the built-in function len for length, which takes in our long sentence value, long sentence. This length function will return the length of the string, so we'll just make sure to print it, output the value, and we get a value of 170. So far, we've only dealt with built-in functions like len or print that perform a specific action. In simple terms, a Boolean type can have one of two values, true or false. That's it, no tricks. How do we assign Boolean type variables? Simple. Let's look at an example in Jupyter Notebooks. This crash course is awesome. We'll set that equal to true. Obviously, I'm a bit biased. And this crash course is not awesome is equal to false. There you go. Booleans in a nutshell. For starters, I highly recommend your variable names be a lot shorter than this. But regardless, we'll go with this for the sake of example. Can this get harder? Of course. The way I just assigned these Booleans isn't very useful. Normally, comparison operators like less than, greater than, less than or equal to, greater than or equal to or not equal to, these comparison operators are often used to produce, to return a bool value. instead of us hard coding something to be true or false. For example, if I set comparison operation is equal to 1 is greater than 2, and I print it, print comparison operation, it gives back false, because indeed 1 is not bigger than 2. That is a false statement. If I replace it with smaller than, it gives back true. Along with comparison operators, we can use logical operators. The three logical operators we'll use are and, or, and not. Let's start with or. If I set comparison operation equal to 1 is smaller than 2, or 2 is smaller than 3, this gives back true, because indeed both comparisons are true. 1 is smaller than 2, and 2 is smaller than 3. If I switch this to 2 is bigger than 3, even though this expression is false, even though we know that 2 is not bigger than 3, this entire operation will still evaluate to true, since with the OR operator, only one of the expressions must be true, and indeed this one is. If I run this, we indeed still get true. However, with the AND operator, if one of these conditions is not true, then the value will return false. Both the first expression and the second expression, they must both be true. We can prove this by running the code, which prints out false, and makes sense, since both comparisons must be true with the AND operator, and indeed this is not the case. 2 is not bigger than 3. However, with the OR operator, as long as one of them is true, then it returns a value of true. The last logical operator we'll look at is the NOT operator. What this does is it flips the bool value. For example, set comparison operation is equal to 1 is smaller than 2. We know that this is 100% true. We know 1 is smaller than 2. But if we add NOT, it flips the bool value to false, giving us false. That is all for Booleans. So far, we've covered 4 fundamental data types: Booleans, strings, integers, and floats. If you're not comfortable with these data types just yet, make sure to complete or redo all the quizzes, since as we move along with the actual self-driving cars content, this needs to become second nature to you. Operators are in and not in. According to the documented definition, in evaluates to true if it finds a variable in the specified sequence, whether it's a string or a list. Otherwise returns false. In contrast, not in evaluates to true if it does not find a variable in the specified sequence, and false otherwise. Let's test this out. Inside of Jupyter Notebooks, I will set a variable months is equal to January, February, and March. Now I want to check, is June inside this list? So I will check if June is in months. If I print this evaluation, and then run the cell, it returns a value of false, because June is not in this list. If I switch this to January, it returns true, because indeed January is in the list. Vice versa, if you put not in instead of in, it would evaluate to false, because we're checking if January is not in the list. Indeed, January is in the list, so this statement is false. The same concept applies to strings, so we'll cover that very quickly. Make a variable course is equal to Python crash course. I will check if the set of characters crash is inside the string. So crash in course. Go ahead and print the return of this evaluation. And this evaluates to true because this set of characters is indeed inside of the string. Change this to rash, and it still evaluates to true because the set of characters rash is also inside the string. If I make this some random variable like a, b, c, d, obviously this is false, and vice versa for not in, because it is not in the string. That is all for membership operators, and an object can be changed, then it's mutable. If an object cannot be changed without creating a completely new object, then that would be considered immutable. This leads us to our next discussion. Lists and strings. We saw that they were very similar data types in the sense that they both share similar methods. However, they are distinct in many ways. Obviously, strings are sequences of letters, whereas lists can be sequence of any data type enclosed in brackets. However, a very subtle difference between the two is mutability. Strings cannot be changed. They cannot be directly changed, whereas lists can. So it follows that strings are immutable and lists are mutable. How can we prove this? Okay, let's start with lists. I will make a variable grocery list is equal to bananas, apples, and cauliflower. Let's assume that instead of cauliflowers, I want rutabagas. I can simply change the element at index number 2 to rutabagas. Simply enough, grocery list at index 2 equals rutabagas. Print grocery list, run it, and indeed the change occurred. Since we were able to change the list is mutable. However, let's try this with a string. Set a variable misspelled vegetable is equal to cucumber. Clearly, I misspelled the word cucumber. This O right here should be a U. Intuitively, what I would think to do is grab the character at index 0, 1, 2, and 3 and change the element at that index to a U. Let's try it. Misspelled vegetable at index 3 is going to equal a U. If we try to print misspelled vegetable, what will happen is that we're going to get an error. Strings are immutable. They cannot be changed. To change a string, you have to create a completely new string. Two things to keep in mind when working with data types. Are they mutable or not? Are they ordered or not? We saw an example of mutability and immutability when we spoke of strings and lists. We discussed how both strings and lists, they are both ordered. Every element or character is in a certain position, and the position of that element is represented by an index. And through the index, we can access that element or character. However, we still haven't worked with data types that are unordered. You'll see examples of unordered data types later on. For now, just keep these two thoughts in mind when working with data types. With a set of indices which specifies a range, the start and stop. The start specifies the index where we want to start slicing the list. For example, if I specify the integer as 1, it will start slicing the list at index 1. The stop integer specifies the index until which we want to stop slicing. If I specify a stop integer of 8, as soon as it reaches the 7th index in the list, it's going to stop. Notice how I said the 7th index, not the 8th index. That's because the upper index is exclusive, meaning the slicing stops at that index minus 1. It's not included in our sliced segment. In this case, our lower index is 1. The lower index is indeed inclusive, and our upper index is 8. So what this will do is it will grab everything from the list at index 1 up until index 7. Let's try this out. Back to Jupyter Notebook. Declare a list ordered numbers is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There is actually an easier way to specify a list of numbers with the range function. I'll show you how to do it momentarily, but we'll just stick with this for now. And let's assume that I want to grab elements from 2 to 9. How would you do that? Well, what we'll do is we'll write out the variable ordered numbers. And to specify indices of the list, remember we need the brackets. The lower inclusive start index will be 2. And we want everything up until and including the number 9. So our stop index will be the number 10. Remember, the number 10 is going to be exclusive, meaning the slicing stops at that index -1, so at 9. Let's output this. Well, let's print it first and foremost. Run the cell, and we get a list that goes from 2 to 9, a sliced list. Let's assume you wanted everything from 0 to 9. Well, you can specify the start index as 0, which will take everything from index 0 up until 9. Alternatively, there is a shortcut where if you omit the starting index, it assumes that you're going to start at the very beginning of the list up until your stop index -1. Let's try it out. And indeed, we get the same results. Let's put 2 back as the start index. So it's going to start at index 0, 1, and then 2. And from that index, we want everything on the list up until the very end, from 2 till 10. We could simply write 11, which is the length of the list. Or if you want to get fancy, we could use the length function to obtain the length of ordered numbers, which indeed is still 11, therefore signifying a stop index of 11. But there is actually a shortcut to this. If you just omit the stop index completely, let's go ahead and do that. It automatically assumes that you want everything in the list beyond your start index. When you run the code, indeed we get the same results. This is perfect and much more concise. If you omit both the start and stop index, it'll just grab the entire list. But then again, why even slice in that case? Before moving on, I did promise that I would show you how to create a list of numbers in a more concise way. We can use the range function. That is, specify a range, and the range will be from 0 to 10. This will create a range from 0 all the way to 9. Even here, the stop index is exclusive. It stops at the number previous to it. And now I can wrap this up in a list data type. If we print it, print the list, it outputs a list in the range of 0 to 9. Super easy and much more concise than actually writing it all out from scratch. We can actually go from 0 to 100. As expected, it gives us a list from 0 to 99. Imagine writing all of this out and hard coding it. That would take a long time. If you don't specify a start index, Python will just assume a start index of 0. So if you omit this 0, we should get the same results. And indeed we do. Let's put this back, as we can also indicate a step size as our third argument. We'll put in a step size of 5, such that it will indeed still contain numbers between 0 and 100, 0 to 99, but it will only include every fifth number in the sequence. If we run this, Clearly, it does so in a step size of 5 numbers. If you change this to 3, the pattern follows. It includes every third number in the sequence, so on and so forth. So range is just another handy built-in Python function that one should be mindful of. Now lists, just like strings, integers, floats, and booleans, it's a data type. However, lists are most similar to strings, as in, they share a lot of the same built-in methods, like length for example. Do note that we can also index strings. To prove this, I will declare a string title is equal to, let's call this show title, is equal to Game of Thrones. If I asked you to grab the third character in the string, the M, well, from what you've learned, G is at index 0, A is at index 1, and M is at index 2. Therefore, you can index it like so. Show title, square bracket, 2. We will print this, and the output is indeed the character M. Just like lists, we can also slice a string, such that if I wanted everything from M up until the very end of the string, 2 would be my start index, colon, and remember, if you omit the stop index, it's going to automatically assume that you want to grab everything beyond your start index. And if we run this, we get Me of Thrones. Mutable. The Google definition is something that's liable to change, something that's changeable. Well, in this context, mutability refers to whether or not we can change something once it's been created. If an object can be changed, then it's mutable. If an object cannot be changed without creating a completely new object, then that would be considered immutable. This leads us to our next discussion. Lists and strings. We saw that they were very similar data types in the sense that they both share similar methods. However, they are distinct in many ways. Obviously, strings are sequences of letters, whereas lists can be sequences of any data type enclosed in brackets. However, a very subtle difference between the two is mutability. Strings cannot be changed. They cannot be directly changed, whereas lists can. So it follows that strings are immutable and lists are mutable. How can we prove this? Okay, let's start with lists. I will make a variable grocery list is equal to bananas, apples, and cauliflower. Let's assume that instead of cauliflowers, I want rutabagas. I can simply change the element at index number 2 to rutabagas. Simply enough, grocery list at index 2 equals rutabagas. Print grocery list, run it, and indeed the change occurred. Since we were able to change the list is mutable. However, let's try this with a string. Set a variable misspelled vegetable is equal to cucumber. Clearly, I misspelled the word cucumber. This O right here should be a U. Intuitively, what I would think to do is grab the character at index 0, 1, 2, and 3, and change the element at that index to a U. Let's try it. Misspelled vegetable at index 3 is going to equal a U. If we try to print misspelled vegetable, what will happen is that we're going to get an error. Strings are immutable. They cannot be changed. To change a string, you have to create a completely new string. Two things to keep in mind when working with data types. Are they mutable or not? Are they ordered or not? We saw an example of mutability and immutability when we spoke of strings and lists. We discussed how both strings and lists, they are both ordered. Every element or character is in a certain position, and the position of that element is represented by an index. And through the index, we can access that element or character. However, we still haven't worked with data types that are unordered. You'll see examples of unordered data types later on. For now, just keep these two thoughts in mind when working with data types. How does that affect the behavior of the data type? If I create a variable name is equal to Amir, that variable holds an immutable string, which is saved in memory. If I assign other name is equal to name, and then reassign name to another value equal to John, this does not affect the value of other name. We can show this by printing print name and print other name. In the results, you can clearly see that even though we updated the value of name, that update was not reflected in other name. Other name retained the initial value of Amir. However, what if we're dealing with a mutable data type? Would we see a different behavior? If we change the data type, well, yeah. Otherwise, what's the point of this video? What we'll do is we'll set books is equal to the Catcher in the Rye, the Mist, and Lord of the Rings. If I set more books is equal to books, and then change one of the books in my list to, let's say, A Song of Ice and Fire, that is, books at index 0, we're going to go from Catcher in the Rye to A Song of Ice and Fire. If I go ahead and print books at index 0, indeed, it equals A Song of Ice and Fire. The list changes such that the element at index 0 is now A Song of Ice and Fire. What if I also printed more books? Print more books. Initially, we set more books to equal books, which held this value, The Catcher in the Rye, The Mist, and Lord of the Rings. But then we updated the first index in our books list. Will that change also be reflected in more books? Let's test it out. Run the cell, and indeed the change is reflected. The take-home message being, since list data type are immutable, changing a list will reflect in all variable names for that same underlying list. Either variable, either name, either label, whatever you want to call it, can be used to change or access that list, all of them holding a reference to it. So that's it for the behavior of mutable and immutable data types. It's very important to be mindful of their subtle distinction, what we just talked about in this video, so that you're always aware of how data is being accessed and configured in your program. Always double check your work and use the print function to make sure that data is being configured the way that it's intended to be. And that concludes our discussion on behavior of simply returns the number of characters or elements in a sequence. Since we're currently working with lists, length returns the number of elements in that list. Back to Jupyter Notebooks, what we'll do is we'll create a list of integers. Numbers is equal to a list of 4, 3, 7, and 4. If we were to take the length of the list, that is, inside of length, declare our variable numbers, run the cell, and the output as expected is 4, since that is how many elements we have in this list. Another function useful for lists is the max method. Max will return the greatest element in that list, in this case 7. We'll test this out by writing max, and the argument will be the numbers list itself. Indeed, it returns 7 because 7 is the greatest numerical value in the list. However, what if I had a list of strings? How would max then work? Well, we can make a list names is equal to whatever names you want. I will stick with Thomas, Geo, and Zach. By taking the max of this list, that is, max names, the output of this is Zach. Why? When dealing with strings, the maximum would be the string that appears last based on alphabetical order. So we can conclude that max works differently depending on which data types you have inside of your list. What if the list contained not just strings, but also numbers? What we'll do is we'll put a 1 in there. In this case, the data types are incomparable. If you try to run it, the result cannot be defined, and as such, the error is shown. Let's revert this back to just having strings, and use the min function. Min, in this case, will do the exact opposite of max. It will return the string that shows up first, based on alphabetical order. In our case, Geo, since G falls before T and Z. Intuitively, for a list of integers, min would simply return the smallest integer, in this case the number 3. The same idea follows for floats. Another useful function that we can use for lists is sorted, such that sorted will take in a value, an argument of our numbers list. If you run this cell, the output is a copy of a list that's sorted from lowest number to highest. By doing the same thing for our names list, sorted names, what this will do when ran, it clearly sorts our names list in alphabetical order, Geo, Thomas, and Zach. We've talked about functions. Now let's talk about methods. Remember, we said that functions accept arguments or argument inside of their parentheses, as you can see right here. This is a function. A method differs from a function in the sense that every data type has its own distinct set of methods. We'll start off by looking at the join method. The join method is actually a string method that takes in as an argument a list of strings. From the string argument, what it's going to do is return a string consisting of every element on that list. All of these elements joined by the string that's calling the method. Here's an example. We'll start off with a hyphen, a string hyphen, which calls the method join, .join, which takes in as an argument, remember, a list. We will have a list of strings. January, February, and March. If we run this code, what it just did is it joined every string in that list with the hyphen string that called the method. Instead of a hyphen, you can make this into a blank space, such that now every string is joined by a blank space. The list of strings is converted to a string, such that every element is joined by the separator string calling the method. In this case, the separator string is just an empty space. Another useful string method is format. This is most easily demonstrated with a print statement. So print, this person is, open up curly braces, close curly braces, do that once more, and another set of brackets. Okay. What we can do now is we can format the string, .format, such that wherever there's a bracket, or a curly brace I should say, we want to replace it with a specific string. That is, inside of format, I can write tall, slim, and blonde. If I run this code, we get the person is tall, slim, and blonde. The string was formatted such that each string over here was assigned to each curly brace according to the order in which they were written. Another useful method is the append method. If you've worked with arrays in other languages, you've definitely seen this method before. What it's going to do is add an element to the end of a list. So we'll copy and paste the list that we have over here and set it equal to a variable called months. Months is equal to the list of strings. What we can do now is append a new month to the end of our list. That is months.append, and we're going to append the month April. We'll go ahead and print months, and we get our appended list, January, February, March, and April. Perfect. There are many more methods and functions that we can talk about. However, this is where we conclude our discussion on, whereas tuples, just like lists, they are immutable ordered sequences of elements. They are used to store related pieces of information. Keyword related, and that information is enclosed in a parentheses. If two values are so closely related that you'll most likely always use them together, use a tuple. For example, back to Jupyter Notebooks, we will set a variable traits is equal to a tuple such that the person is tall, slim, and blonde. This tuple you see right here, it's similar to a list in the sense that in this case, it encapsulates an ordered sequence of strings where each of them can be accessed by their index. For example, you can set height is equal to traits at index 0, and build is equal to traits at index 1. We can go ahead and print height and build, and everything works out accordingly. Now, unlike lists, we cannot change tuples. They are immutable. We cannot add or remove elements from a tuple without creating an entirely new object. Oftentimes, parentheses are omitted when declaring tuples. If we omit them, everything should still work out the same way. They are completely optional, and it's up to you whether or not you want to keep them, depending on if the parentheses are useful in clarifying the code. One last thing I want to demonstrate before we end this discussion is tuple unpacking. Before doing so, it's important to note that while we were successful in assigning all the elements of a tuple to multiple variables, there is a more compact way of doing it. That is, we could have simply used the comma notation to write height, build, hair is equal to traits. This would respectively assign tall to height, slim to build, and blonde to hair. We can actually shorten this even further if we don't need to use the traits variable directly, by setting height, build, and hair equal to tall, slim, and blonde directly, and deleting that. This is called tuple unpacking. It assigns the contents of our traits tuple to multiple variables without having to make multiple assignment statements. That ends our discussion on tuples. When we delve deeper into the actual self-driving cars course content, you're going to encounter tuples quite often, so it's important that you're aware of the syntax. Type, just like a list, is mutable. Except in a set, elements are unique. What do I mean by this? Well, I'm going to create a variable, duplicate numbers is equal to 1, 1, 2, 2, 3, and 3. This list has duplicate numbers. What if we were to convert this to a set? Set unique numbers is equal to a set of duplicate numbers. Go ahead and print unique numbers. Going to make this into a plural. Run the cell, and it prints out 1, 2, and 3. By making this list into a set, it removed the duplicate elements from our list. Hence why a set is a collection of unique elements. This collection of elements is also mutable, meaning we can change it. Set has a built-in add method, which is similar to the append method that we saw earlier for our list. To our unique numbers set, we will add unique numbers dot add, and we will add the number 4. If we print the set now, print unique numbers, it should give us 1, 2, 3, and 4. It added that number. What distinguishes add from append is that if I try and add an element that already exists in a set, it won't actually add it, since a set is composed of unique elements. When I ran this cell and tried to add the number 3, indeed it didn't do it. That is pretty much all we're going to cover for sets. Just remember that sets are unordered, so we cannot use an index to represent the position of an element inside of a set. We can check if an element is inside of a set with the membership operator in. If you were to try and print 2 in unique numbers, such that we're checking if 2 is inside of the unique numbers set, it returns true because indeed it is a part of the set. There are many operations that can be done with sets. However, this is where we will conclude our discussion and move composed of unique keys. Each unique key corresponds to a value. Even though dictionaries themselves are mutable data types, that is, we can add, change, or remove key value pairs as we please, the keys themselves that compose the dictionary, they must be unique and of an immutable type, either string, number, or tuple. Let's look at an example. In the Jupyter Notebook app, we'll declare a dictionary by setting a variable inventory is equal to curly braces. Dictionaries in Python are denoted by curly braces. Inside these curly braces will have key value pairs, such that the keys will be grocery items and the value the price of an item. So, bananas, they will have a price of $1.29, $1.29. Apples, they will be priced at $2.99 a pound, and papayas, $1.39. And there you have it, key value pairs. The key is an immutable string type, a grocery item, and the value in this case is just a number, a price corresponding to the grocery item key. Dictionaries are not ordered. If you remember with lists or tuples, they were indexed by a range of numbers. Dictionaries are indexed by their keys, meaning I can access a specific value inside of my dictionary by referencing its corresponding key. If I were to print inventory with key bananas and run it, I should get 129. Not only are dictionaries unordered, but we can also change their values. They are mutable. Let's assume the price of bananas went up. They are now $2.99 a pound. What I would do is access the dictionary value based on its key. So, inventory, bananas, and now I can change the price, the value corresponding to the bananas key, to make it equal to $2.99. After changing it, if I print inventory, bananas, it is indeed now $2.99. The value was mutated, it was changed. Dictionaries also have a useful built-in get method, which gets the values. It looks up the value at that specified key. If the key you specified doesn't exist in the dictionary, then it would just return none. Let's try it out. Make a variable, bananas price is equal to inventory.get, and I will get the price of the bananas. Print bananas price, and it would get the value of $2.99. Otherwise, if I put some random key, like strawberries, we'll declare a strawberries price variable. If I try to obtain a random key that doesn't actually exist in the dictionary itself, and print the results of this get method, it would bring me back none. We don't have a price for this yet. We can also check if something is inside of a dictionary. In our case, I want to check if we have a price for papayas. You probably guessed it, we need the membership operator in. So we'll print papayas in inventory. It will check if we have a key papayas inside of our dictionary. Run the code, and of course we do, it's right here. If I try out some random key, let's say celery, it returns false. In summary, dictionaries are an unordered set of key value pairs, such that every key must be unique. A pair of braces is used to denote a dictionary, such that the dictionary's main purpose is to store and extract values based on their key. That is all for dictionaries, not just price. For every key in my dictionary, for every item, I want its value to represent not only the price, but the country of origin. This leads us to our next discussion, compound data structures. Back to Jupyter Notebooks, instead of just price, we'll declare another dictionary for each value, such that each grocery item will have a price. In this case, for bananas, it will be $2.99, and a country of origin. Bananas, I believe, come from Guatemala. We'll do the same thing for every other grocery item, for apples and for papayas. Let's go ahead and separate this. Let's reconfigure the prices. Apples will be at $1.29 and papayas $2.39. Apples will come from United Kingdom, and papayas will come from Costa Rica. All right, that is it for compound data structures. Nothing difficult, just a key which corresponds to values that are also dictionaries. If I were to print grocery items for the key apples, it gives us the value at that key to be a price of $1.29 and a country of origin of the United Kingdom. Much more informative than how we had it previously. What if I wanted to access just the country of origin of the apples? This is very important. To access the value in this dictionary, we have to grab it based on its key. So just add an extra set of brackets. Country of origin. Run the code, and it provides us with the grocery items as country of origin. First, we're looking up the key apples, which returns this dictionary. And then, from this dictionary, we're looking up the key country of origin, which returns this value and prints it. That is all for this video. An if statement runs or skips code based on its conditional statements. You never want to run code in a top-down approach. Some code should only be run based on existing conditions. Otherwise, it should be skipped. Let's have a look at an example. Remember this dictionary we had earlier? We used it to identify the price of each grocery item. We also talked about the membership operator in, and how it can check if something is inside of a dictionary or not. So what we'll do is we'll declare a string item. For now, it will just be Brussels sprouts. And now we'll check if item in grocery items. If the item is inside of our dictionary, then we want to execute some code. For now, I'll just print found the item. There's one thing here that's very important and that I want to point out, and that is the indentation. In most programming languages, indentation is just a way for your code to look more readable. In Python, however, instead of using brackets to indicate scope, indentation is required to indicate what block of code a statement belongs to. In this case, the print logic, because it's indented in such a way, it belongs to this if statement. Notice how when we press enter after the if statement, it creates that indentation for us. In summary, much of your code's logic will depend on white space, so be careful how you indent your code. If we were to run this code, nothing gets called. Why? Well, the item is not inside of our dictionary. We don't have Brussels sprouts in there. This if statement evaluated to false, and it skipped this block of code. Although we need to let the user know if it skipped it or not. So we'll add an else statement, such that if this if statement evaluates to false, this code is skipped, and the code belonging to the else statement will then get called. In else, we'll print could not find the item. And there you have it. We can actually take this one step further, such that in the else statement, if the item does not exist in our dictionary, which it doesn't, we'll update our dictionary to have the item. That is, grocery items dot update, and we'll add a new key value pair. To do that, make sure to write your curly braces to indicate it as a part of the dictionary. The item that's passed in is going to be the key, so Brussels sprouts, and we'll give it a default price of $2.99. We're not too concerned with the price at the moment. And right after updating the item, we'll print just added the item. Here is the updated grocery list. And we'll pass in our grocery items dictionary. Run the code, and it works out as expected. The item at first is not in the dictionary. This if statement evaluates to false, so its block of code is skipped. The else statement then gets called, adds that item to our dictionary, and prints out the following statement. What I want you to take away from this video is not so much dictionaries, but conditional statements. If not, the code inside of the else statement was triggered instead. Now we'll look at elif statements. Let's assume that an if statement fails, yet we're still not ready to move on to the else statement. We want to test one more condition, or a few more conditions. And if those conditions are true, we want to invoke a separate block of code before moving on to the else statement. That's where elif comes in, and we'll make use of it momentarily. Let's continue on from our previous lesson, and instead of just setting item equal to Brussels sprouts, actually we'll change this from Brussels sprouts to rutabagas, and we'll set a price for rutabagas equal to $2.99 on the same line of code. If you're not familiar with this notation, please refer back to section 1 of the crash course. The way this code is currently set is that if an item is not in the dictionary, the if statement is false, the else clause is true, and it updates the dictionary with that new item. And you know what? Instead of setting $2.99 directly, we'll set it equal to our variable price. What we'll do now is we'll add an elif statement. Elif price is bigger than $2.99. We want to tell the user, or in our case, we'll just print too expensive for inventory. If we run this, clearly the else statement still gets called because rutabagas is not in our grocery list and the price is clearly not bigger than $2.99. I'm going to rerun the first cell to restore the initial value of grocery items, and now I'm going to increase the price of rutabagas. Rerun the code. First of all, the if statement gets skipped because this condition is still false. Rutabagas is not in the initial value of our grocery items dictionary. However, this evaluates to true because the price is indeed bigger than $3.99. Because the price is so expensive, we're not going to add it to our inventory, thus the elif statement gets called. This evaluated to true and ran the block of code corresponding to the elif statements. This is also the first time we've made use of a comparison operator inside of an if statement, or an elif statement for that matter. There are other comparison operators like equal equal, is not equal, bigger than, which we just saw, smaller than, greater than or equal to, and smaller than or equal to. The names of these operators kind of gives away their functionality. Let's look at one more example where we can make use of the is equal comparison operator. We'll start on a new cell and create a variable named daytime is equal to dawn. And what we'll do now is we'll write if daytime is equal to dawn, make sure there's two equal signs, not one, in order to indicate a comparison operation, not an assignment. So if daytime is equal to dawn, then we're going to print still asleep. Note the indentation to make sure that this block of code belongs to this statement. Elif, else if daytime is equal to morning, then we'll print time to go to work. Elif daytime is equal to noon, we'll print time to take a lunch break. Elif daytime is equal to afternoon, print time to go home. And finally, we'll put an else statement. So if it's none of these daytimes, it could be nighttime, midnight, whichever, we'll simply print time to go to sleep. So the purpose of this exercise was not only elif statements, but also for you to remember to use double equal signs when making a comparison. Do not ever confuse the double equal sign comparison operator with the single equal sign, assignment operator. If you want to make a comparison, as we are doing here, use a double equal sign. If you wish to assign a value to a variable, use only one equal sign. It's very important to be able to distinguish between the two. Let's end this tutorial by running our code, and it prints still asleep. Since this if statement evaluated as true, this block of code is run, and all of these ones are thereby skipped. If I change this to noon, run the cell, this block of code is skipped, and now this is ran because this evaluates to true. If I change this to nighttime, none of these get called, and this gets invoked. Before I end this tutorial, I really want to stress code indentation. It's how we tell Python what code is inside the if statements, and what code is outside of it. This code is indented such that it corresponds to this if statement, so on and so forth. Indentation convention typically follows 4 spaces. Whatever amount of spaces you're using, it's important to stay consistent throughout. Otherwise, your code will have a different meaning than what's intended. When studying the flow regime of some fluid inside of a pipe, if the Reynolds number is between 2000 and 10,000, this flow is transitional. If it's under 2000, the flow regime is laminar. If it's over 10,000, it's turbulence. We're going to focus on the transitional part of the regime. Back to Jupyter Notebooks, declare a variable Reynolds number is equal to 5,000. To check whether or not this value corresponds to transitional flow, we're going to use multiple comparison operators. That is, if 2000 is smaller than the specified Reynolds number, whatever that may be, and if it's also smaller than 10,000, if Reynolds number is between 2000 and 10,000, we're going to print flow regime is transitional. And that is it for using multiple comparison operators. To check if a value is between 2 other values, and all of that done inside of a single if statement. You'll come across situations like this quite often. If we run the code, indeed this flow is transitional since it lies between 2000 and 10,000. Now if I change it to something that exceeds the range, for example 11,000, the if statement returns false. It does not lie between the specified range, and this code is therefore not invoked. This could have also been done with a logical operator. Instead, we could have written if Reynolds number is bigger than 2000 and Reynolds number is smaller than 10,000, print flow is transitional. In this case, the Reynolds number must be greater than 2000 and also smaller than 10,000 for this to return true. If one of these is false, if one of these evaluates to false, then the whole statement is false and this code is skipped. If we run the cell, clearly the code is skipped because this condition is not satisfied. 11,000 is not smaller than 10,000. Let's change this back to 5,000. I'm going to rerun this cell, and we're back in business. It satisfies both conditions of it being bigger than 2,000 and smaller than 10,000. Note how both if statements have the exact same results since they specify the same conditions, but just in different formats. Another operator that's often used is the OR operator. The OR operator, as we've seen previously, unlike the AND operator, only one of the conditions has to evaluate to true. So what we'll do, inside of a new cell, we'll write if Reynolds number is smaller or equal to 2000, or Reynolds number is bigger or equal to 10,000, then we can say print flow is not transitional. I'm going to change Reynolds number to 1000. Rerun everything, including the cell. Clearly the code is invoked because this condition is satisfied. It returns true, whereas this one is not. However, with the OR operator, only one of them needs to be true for the code to be invoked. This makes sense in our case because the Reynolds number is smaller than 2000, meaning that it's laminar and thus not transitional. If it's bigger than 10,000, it would be turbulent and also not transitional, as this condition would then be satisfied. So long as one of these conditions is true, with the OR operator, this code is going to be invoked. That sums it up for complex Boolean expressions. You learned all about if, else, and elif statements, the for loop, and the while loop. We'll start this off by using the for loop. A for loop can loop through, can iterate through, over any iterable. What is an iterable? Well, as the name suggests, anything that we can iterate through. Anything that can return one of its elements at a time. That includes lists, strings, dictionaries, tuples, etc. We'll start our example by iterating over a list. In Jupyter Notebook, declare a list months is equal to January, February, and March. We can iterate through this list by using a for loop. That is, by writing for month in months. So for every month inside of our months list, we're going to print the month. This variable month corresponds to the month inside of our list that's currently being iterated through. If I run the cell, clearly it looped through our entire list, and one at a time it printed January, February, and March. Notice how this line of code is indented, and that's because, just like how we had it with if statements, this corresponds to the body of the for loop, such that this indented block of code is invoked once for every single element of our iterable, and each element, at the moment that it's being iterated through, is represented by an iteration variable that we explicitly declared to be called the month. You can name your iteration variable anything you like. A common recommended pattern is to name it something that's singular to our list, as we did here. We can also iterate through a range. We saw ranges in the slicing video when we learned how to create a list from a range of numbers. Well, we can iterate through a range of numbers by simply writing for number in range 0 to 100. And then we're simply going to print all the numbers from 0 to 99. That is, print number. Run the code, and clearly it iterated through our entire range, and one at a time it printed 0, 1, 2, 3 all the way till 99. And each number, at the moment that it's being iterated through, is represented by the number iteration variable when it's being printed. So far we looked at two iterable types that we can loop through, ranges and lists. Do note that we don't always have to make use of our iteration variable. You can print something like hello, for example. It doesn't matter. For loops so far, we've used them to extract elements. We can also use them to create elements. We'll demonstrate this by creating a variable, names, is equal to a list. My list will be Hillary, Diana, and Brian. Our end goal is to capitalize all of these names. We're going to modify this list with a for loop. To start this off, a common way to modify lists is with the range function. So what we'll do is we'll iterate through the range of this list and grab the index of each element. So we'll write for index in range, and the range will have our list length, and the argument will be the names list. The range will be the length of our names list. If you remember from before, range takes in a start index and a stop index. In this case, all we put in was a stop index, which right now equals 3, the length of our list. Since we omitted the start index, Python will assume a start index of 0 that goes all the way till 2. Why 2? Why not 3? The length is 3. Remember, the stop index is exclusive, meaning that the range will stop at the number that's previous to it. Therefore, the range will go from 0 to 2, which matches the indices on our list, 0, 1, and 2. If you're not too sure how start, stop, and step works, make sure to revisit the slicing lecture. Anyways, if we print index, indeed, the result given is exactly what's predicted. We can actually use the index of each element to point to that element that's in our list and capitalize it. To do so, write names index is equal to names index dot title. The method title returns a copy of the string in which first characters of all the words are capitalized. So in the first iteration, the index is 0, which means that we're pointing to the first element in our list, Hillary. We're going to modify the first element of the list to make it equal to a capitalized version of Hillary, thanks to the title method. This loop is then going to iterate twice more and do the exact same thing for Diana and Brian. After the for loop, once you're done modifying the list, we're going to print names. Notice how there's no indentation here, because this print statement will occur after the for loop. It doesn't belong to it. Let's run the code. And there you have it. It iterates through the list 3 times, capitalizes each element, and then prints the updated version. That is all for looping through lists. Declare a dictionary, movies, which will equal, open up curly braces, Titanic. And Titanic, I believe, was released in 1997. As well as we'll have another entry of Finding Nemo, another key value pair, which was released in 2003. If you don't know what a dictionary is by now, please refer to the dictionaries tutorial in part 1 of this crash course. Anyway, looping through dictionaries is different in the sense that there are 2 ways of doing so. You can iterate through just the keys or both key value pairs. Iterating through just the key is done like so. For key in movies, print key. If I run the cell, it iterates through our dictionary, and one at a time it prints the keys, such that each key in our dictionary is represented by a key iteration variable that we explicitly declared. If you want to access both key and value, simply add another iteration variable. You can call it whatever you want, although best practice is to just call it value. There is still one more step if you wish to iterate through both keys and values, and that is to use the built-in methods items. Like so. We need items since it returns a list of the dictionary's key value tuple pairs. So go ahead and print value now. Run the cell, and clearly it outputs both key value pairs. We can actually get a little fancier than this by using the string format method. If you forgot what format does, first we'll declare a string inside of our print statement, and that string will be the movie, open up curly brace, close curly brace, was made in another set of curly braces. What we can do now is we can format the string .format such that the first bracket will be replaced by our key and the second bracket will be replaced by our value. Run the code and it iterates through every key value pair for each one, printing a distinct sentence. That is all for for loops. Our difference. While loops have an indefinite amount of iterations, in the sense that the amount of times a while loop will iterate through a block of code depends on your code's logic, and whether or not a certain condition is met. If you're not careful, the while loop could go on forever. So, rule of thumb, a for loop iterates through an iterable, and a while loop iterates based on a condition. While a condition is true, the while loop will invoke its block of code repeatedly until the condition becomes false. In Jupyter Notebook, I'm going to declare a variable, random number is equal to 20. Subsequently, declare that while random number is smaller than 30, then print random number. Once again, notice the indentation, which indicates that this print function belongs to the body of the while loop, just like we saw with for loops and if statements. If I run the code right now, it's going to get executed forever. Why? Well, this condition is true no matter what. 20 is always smaller than 30. We're not doing anything in the body of the while loop to change this value. So this condition will always be true. Let's go ahead and restart the current kernel. We're going to shut down the kernel. Comment out this block of code with the keys command /. We will restart our kernel and run all the cells. So now, inside the body of our while loop, let's uncomment our code, and inside the body of our while loop, we'll specify it such that for every iteration, we'll increase the value of our random number by 1. That is, random number plus equals 1. Remember the plus equals assignment operator. It takes the current value and increments it by 1. So for every iteration, we'll increment our number by 1 until it reaches 30, until the number becomes big enough for this condition to be false. Run the code, and it iterates through our code 9 times, incrementing our number 9 times. Once the value becomes 30, clearly the condition is now false. This code will not be triggered for that value and the loop breaks. That is it for while loops. The continue statement jumps over one iteration of the loop. It skips one iteration of a loop. Whereas the break keyword jumps out of the loop completely. It terminates it. If we detect that a certain condition has been met and we don't need to iterate through our code anymore, then we break out of the loop. Let's look at an example. We'll start off by making a list number, a list of numbers, is equal to a list which ranges, we're going to have a range from 0 to 10. You should know what this is by now. Simply a list of numbers that goes from 0 to 9. If you're not sure why, make sure to revisit the video on slicing. We'll print this list for clarity. Print numbers. There's our list. Now on the second cell, we're going to loop through this list with a for loop. For number in numbers, and inside of our block, every time we iterate through this list and access each individual number one by one, we'll declare an if statement. So if number modulus 2 is not equal to 0, If our number divided by 2 does not give us a remainder of 0, if the number is odd, we're going to continue. And outside of the if statement, we're going to print the number. The logic being, if we're looping through an odd number like 3, this condition will evaluate to true since the modulus will not be 0. Continue gets invoked and skips over the loop, and nothing below gets called. Otherwise, if we're iterating through an even number, a number like 2 or 0, continue is not invoked as this would evaluate to false. It does not skip over the loop body, thereby printing the number itself. If you run the cell, indeed we end up getting 0, 2, 4, 6, and 8. Since every time we iterate through an even number, it skips over the continue keyword, therefore executing the code inside of the for loop body. If we replace this with a break keyword, as soon as we iterate through an odd number, it would just terminate the entire loop. Run the cell, and clearly it first iterates through 0, an even number. This condition is false, break doesn't get called, and the iteration goes without interruption, printing the number 0. But then we're iterating through the number 1, that's an odd number. The if statement evaluates to true, breaking the entire loop. The same concept applies to while loops. Named section of your program that performs a specific task. That way, when you want to execute a specific task, all you have to do is call the function. This highlights one of the most important reasons that programmers use functions. Reusability. Once a function is defined, it can be used over and over again, without having to worry about any of the specifics needed to accomplish the task. This will be a lot more clear once we dive into it, but that being said, we'll learn all about functions, scope, docstrings to document our functions, and finally we'll also look at anonymous functions with lambda expressions. I'll see you in there. Function of your program that performs a specific task. One of the main reasons why functions are so useful is reusability. Once a function is defined, it can be used over and over and over again. Without having to constantly copy and paste your code, you can simply call your function. You can invoke the same function many times in your program, which saves you a lot of work. How do we define a function? Simple. To define a function, start with the def keyword. As in, we're defining a function. We're declaring a function definition. Then comes the name, the function name. I want to define a function that calculates the area of a rectangle. So I'll call it rectangle area. The area is dependent on length and width. So immediately after the name, you would put parentheses that include these arguments, length and width. The arguments, the length and width, are passed in as the function is called, where they can then be used inside of the body of the function. Let's dive into Jupyter Notebooks to see this in action. As previously noted, the first step is to obviously declare the function definition. We'll start this off with the def keyword. The function name will be rectangle area. Next comes the parentheses, which in our case is going to take in 2 arguments. Functions don't have to take in arguments, but we will have 2 of them that are length and width. We discussed this previously. And just like if statements as well as loops, to open up the block of code that corresponds to our function, we need a colon, followed by indentation. Any code within the indented space belongs to the body of the function. And what we'll do is, inside the body, we're going to set a variable name area is equal to length times width. Misspelled width. Whatever length and width that the user inputs when they call the function, they will be multiplied to obtain the area. And now all we have to do is simply return the area. Return area. We can actually do this in a single line of code by directly returning length and width and getting rid of this line. Very concise and, more importantly, reusable, because now I can simply call the function like so. On a new cell, I will call the function rectangle area. The length will be 2 and the width 3. If we print the value of our function call, the return value, what it's going to give us is the area. Run the cell and it prints 6. In essence, we called the function rectangle area, passed in our length and width as arguments, which were evaluated inside the function definition, and returned a value of their product, which was 6, thereby printing this return value. If you've ever programmed before, this should be very familiar to you, aside from the change in syntax right here. Before wrapping up this video, we can actually print the area directly inside the function. We don't actually need a return value. We can do so by first deleting this print statement here, delete the return statement, and we're simply going to print inside of our function definition length times width, the area. If I call the function again, rectangle area, this time I will pass in the same length and width, 3 and 2. The arguments that were passed in are multiplied and printed. This function obviously is reusable, so we can call it as many times as we want. I will copy and paste this function call 3 times. Let's print the area of a 4 by 6 rectangle, a 3 by 9, and a 2 by 2. Run the cell, and we get 24, 27, and 4. Perfect. All of the areas that were required. That is all for function definitions. Obviously, the logic can be a lot more complex than that. We can have all kinds of if statements and loops going on in here, but the main idea that I want you to take home is that this is a reusable chunk of code. In any programming language is a region of the program where a defined variable can have its existence, and beyond that, the variable cannot be accessed. In this lesson, the local variables will be function scoped. That is, variables created inside of a function, they can only be accessed within the block in which they are declared. A global variable, however, can be accessed in every part of the program. Back to Jupyter Notebooks. If I define a function, def random function, with no arguments, and inside the function I create a variable, name is equal to Bill. That variable name that we created inside the function can only be used within that function. It is scoped to this function. Accessing it outside the function is not possible. If I try to print name outside the function, we will get an error. Name is not defined. It is only defined within the scope of the function. On the other hand, we talked about global variables. If I declare a variable number is equal to 2, the number variable can be accessed anywhere. It is not scoped to any function. It is global scoped. If I print number, everything works out fine. The function is reusable whenever we want to calculate the area. Instead of writing the formula down over and over, we can simply call the function rectangle area as many times as we want, and thereby calculating the area for as many dimensions that we choose to specify. This is a very simple example. However, when your code gets larger, you're going to have a lot more functions, and oftentimes you'll be working with a team of developers. To them, it won't be clear what the purpose of your functions are. That's why docstrings can be used. Docstrings are a type of comment used to explain the purpose of a function and how it should be used. It documents your code. Back to Jupyter Notebooks, to declare a docstring, you must declare triple double quotes, like so. In between the triple quotes, you can now write anything you want. Whatever you feel best describes your function. The rectangle area function is very simple. So I'm just going to write calculates area of a rectangle. However, if you're dealing with a more complex function, sometimes a longer description is more appropriate. If you want to get super descriptive, a more common convention is to explain a function by using the input and output descriptions. The input in this case would be like so. Input. This function takes in two parameters, length and width. And the output would be this function calculates the area based on the length and width provided by the user, where area is equal to length times width. We may have went a little over the top in explaining this very simple function. If you want to do it the way we did it previously with a single sentence, that's perfectly fine as well, so long as you think it provides sufficient documentation. Back to Jupyter Notebooks, declare a list of numbers is equal to 1, 2, 3, 4, and 5. Alternatively, I could have used the range function to create this list, but regardless, what we want to do is filter out any number that's odd. With your current knowledge, you could use a for loop, iterate through this entire list, check if the number is odd with an if statement. If it is, remove it from the list based on the index. We did something very similar to this before when we modified lists based on for loops, but that would be a little tedious and not very concise. There is a much easier way, and that is to use the higher order function filter. What we'll do is we'll write filter to denote the filter function, and the first argument of this filter function is, guess what? Another function, which makes sense since we're dealing with a higher order function. More specifically, it takes in a function that returns a Boolean. So what filter will do is it will go through every single element of our list. For every element that it iterates through, it's going to pass it into our function. In our case, the function will evaluate whether or not the number that's being iterated through is even or odd. If the number is indeed even, the function will return a value that evaluates to true, telling the filter function, hey, we're going to keep this value. Otherwise, if the number that's being iterated through is odd, the function will return a value that evaluates to false, telling the filter function, filter out this number, get rid of it. Now that we went over the theory, let's execute it. We're going to make a function def, even, or odd, which takes the number that's being iterated through. We're just going to call it number. That's the argument. And that function will return number modulus 2 is equal to 0. Make sure this is a double equal sign since we're declaring a comparison, such that we want to check if the number being iterated through, is it even or odd? If it is even, it will evaluate to true and it will tell the filter function to keep the number in the list. Otherwise, it will evaluate to false and the filter function will know to remove the number. Obviously, the next step is to actually invoke this function inside of filter, even or odd. And careful, do not specify a parameter inside of the filter function. The second argument of the filter is the iterable that we want to filter from. In our case, the list, the numbers. Finally, we just have to convert this back to a list by enclosing it with a list type. And if we print this, run the code, it outputs 2 and 4. It removed all of the odd numbers. It iterated through every number in our list and for every iteration, it checked to see if that number divided by 2 does it give a remainder of 0. Is it even or is it odd? If it was odd, if the remainder was not 0, the function returns false and the number is thereby filtered out. And we get our even numbers. There is one problem with this. Remember what we talked about earlier. Functions should be reusable chunks of code. If you're just going to use it as an argument in a higher order function, it's not really reusable. That's why in this case we use the lambda operator. The lambda operator provides a way to create small anonymous functions, functions without a name. They are helpful for creating quick functions that aren't needed later in your code. How do we create a lambda operator? Well, first we need the lambda keyword, lambda. We need the lambda keyword to indicate that this is a lambda expression. Following lambda is the argument that's passed in from the higher order function. In this case, we'll just call it number. Similar to functions as well, following that is a colon. And finally, what comes next is the expression that's being evaluated and returned. In this case, we're returning a Boolean expression that checks whether or not the number being passed in from the filter function is it even or odd. If it is even, it evaluates to true, otherwise false. So just copy and paste that, and we should be good to go. Notice how we don't need to specify a return value inside of a lambda expression. This is much more concise. If we delete this, run our code, we get the exact same results. This acts the same way as our regular function did. There are obviously a lot of higher order functions in Python, like map and reduce. We're not going to discuss all of them. You will come across them later on in the course, although they are more convenient when dealing with numeric operations. A one-dimensional or multi-dimensional array generally consists of a homogeneous grid of values that are all of the same type, whereas lists would be the Python equivalent of an array, but are heterogeneous in the sense that they generally contain elements of different types. This is the most obvious difference. A more subtle difference lies in their functionality. NumPy arrays allow vectorized operation, such as element-wise addition and multiplication, which is a lot more concise than how it would be done with Python lists. Its concision ensures clean code when dealing with numerical operations. Let's have a look in Jupyter Notebooks, where we compare vector addition with plain Python code versus vector addition with NumPy. We'll create two lists with the range function. Make a variable, list2 is equal to a list that ranges from range 1 to a stop integer of 4. Recall that the stop integer is exclusive, stopping at the integer previous to it. And set another variable, list3, equal to a list that equals the same thing, range from 1 to 4. We'll set one more variable, list_sum, equal to an empty list for now. There is a reason why I named one list2 and the other list3. The goal is to raise every element in the first list to the power of 2, yielding 1, 4, and 9. And every element in the second list to the power of 3, yielding 1, 8, and 27. Then we want to add these two lists, resulting in the list sum of 2, 12, and 36. We'll first try this with Python lists, and then we'll do it with NumPy arrays. With our list, what we'll do is we'll declare a for loop. For index in range 3. The number 3 corresponding to the length of both lists. We made 3 our stop integer, that way the indices that we'll iterate through will be 0, 1, and 2. If you're not familiar with what we're doing at the moment, make sure to look back at the Python crash course where we discussed for loops. I can then access and modify each element on both lists with the index that's being iterated through. We'll start with list2 index. So every element on list 2, according to the index that's being iterated through, we're going to set it equal to itself. List2 index, but we're going to set it equal to itself raised to the power of 2. We'll also do list3 at index. We'll set that element equal to itself raised to the power of 3, giving us the required values. Inside the for loop, for each element that we're modifying in list 2 and list 3, we'll add them up and append it into our list sum. That is, list sum dot append will add both elements that are currently being iterated through and modified. List 2 at index plus list 3 at index. And now outside of the for loop, if you print the sum, print list sum, we get 2, 12, and 36. Now that was a lot of work. There is a reason why NumPy is known to be a lot more convenient in numerical operations. Because with NumPy arrays, all of this could have been done with 3 lines of code. No looping necessary. We'll give it a try. To begin using NumPy, we'll have to import it. Import NumPy as an alias np. This imports all the submodules and functions from NumPy, which can be accessed from the alias np. We'll first make use of the NumPy arrange function. We'll set array2 is equal to NumPy np.arrange 1 to 4. Arrange is very similar to the range function that we saw in the Python crash course and are currently seeing right now. They are similar in the sense that they both have a start, a stop, and a step, even though so far in this lesson we've only made use of the start and stop integers. The stop integer works the same way as it would for range. It stops at the integer previous to it. So we're going to have a sequence of integers 1, 2, and 3. The main distinction between the two is that range would create a list from 1, 2, and 3, but arrange creates an array from 1 to 3. We can print this for clarity. Print array2, and indeed that is what we get. It's very important to recognize this is an array, not a list. Notice an array doesn't have any commas. The array is a specialized data structure intended for numerical data. We'll discuss it in more depth in the next lesson. For now, this is an array, and to raise every element of this array to the power of 2, all I have to do is just raise it to the power of 2. Run the cell, and this works out perfectly. It raises every element in the array to the power of 2. If you try doing this with a list, we'll comment this out for now and raise one of the lists to some power, and Python yells at us we're not allowed to do that. That's one advantage of working with arrays. We will do the same thing for the second array. Array3 is equal to, copy and paste the following, and we'll change this to a 3. We're setting all elements of this array to the power of 3. And if we print this, print array3, accordingly it outputs an array with each element raised to that power. Finally, we just need to add the elements of these two arrays. We'll delete these print statements for now. And we're just going to print array2 plus array3. Run the code and it outputs the expected result, all within 3 lines of code. If you tried to add 2 lists, as we saw in the Python crash course, it would simply concatenate them. Whereas with arrays, it took the summation of each homologous element. Before we end this discussion, we talked about element-wise addition and exponents. But some other operations that we can take advantage of are subtraction, multiplication, and division. However, aside from basic mathematical operations, NumPy also offers us a wealth of universal mathematic functions that we can use to operate on our array. All of these universal functions performing element-by-element operation over our array or a set of arrays. We'll go over that later on. For now, we'll go over some common mathematical functions accessible to us through NumPy. The first one being numpy, or np.power. What this does is it will raise all the elements of our array by a corresponding power. np.power, the first argument is the array itself. We're not going to use the arrange function this time to make our array. We'll try another method. On the basis that in general, numerical data arranged in an array-like structure in Python, such as a list or a tuple, those can be converted to arrays through the use of the array function. Array, taking in a list or a tuple, whichever one you want, a list of 1, 2, and 3. This will convert our list to an array. Now that we have our array, the second argument will be the corresponding power. It will be to the power of 4. If we run this, array is not defined. I forgot to add the np alias, which gives us access to all the submodules and functions from NumPy, so don't forget to add your alias np. If we run this again, notice our list enclosed by the array function. Indeed, this is an array because if we print it, outputs the array itself. Now, alternatively, we could have just written np.array and raised it to the power of 3, as we did previously. This would have worked as well. But it's good to be mindful of universal functions. We'll revert this back. Another commonly used function is numpy.negative. The first argument being our array itself. We'll just copy the array that we have over here. This function speaks for itself as it simply returns an array with negative values. Forgot a parentheses, and there you go. Let's also print this. And now, notably, we have access to the exponential function, np.exp. And we'll take the exponential of every element in our array. And you know what? Instead of copying and pasting this over and over, what we'll do is we'll create a new cell with Alt-Enter and set a variable sample array is equal to np.array 1, 2, and 3 and replace it at every instance. And now we'll take the exponential of every element in the array. And indeed it does take the exponential. We can also use the log function, np.log, which takes the natural logarithm of each element in the array. We can output this and it takes the natural log. We can also make use of trigonometric functions. All trigonometric functions use radians when an angle is called for. Recall that the ratio of degrees to radians is 180 over pi. We can take the sine of all elements in the array, np.sine, sample array, and it takes the sine of every single element. This was a very simple example of why NumPy is more convenient than normal Python code when it comes to numerical operations. We first demonstrated that vector addition is clearly a lot easier with NumPy, such that we're also given a wealth of universal functions that we can use to operate on these arrays, element by element, all of which can be accessed in documentation. With NumPy, indeed, there are many mathematical functions that will make our lives easier. A lot of vector and matrix operations are available to us. However, it also goes beyond convenience, as NumPy arrays also have smaller memory consumption and high performance relative to their Python list counterpart, ideal when reading or writing from several large terabyte files. Now that we know why we need NumPy, that is, the items that it's composed of are all of the same type. An n-dimensional array is defined by its shape and the item that it's composed of. The advantage of all items being the same data type is that now you know every item has the same size block of memory, each block of memory in the array interpreted the same way. This makes it easy to determine the storage size required for the array. Let's start by discussing the shape. The shape of an array represents a tuple of array dimensions. For a one-dimensional array, the shape would be a tuple of only one value n, where n is the number of elements in your array. For a 2D array, the shape would be nm, where n is the number of rows and m is the number of columns. In the last video, when you created your array with the arrange function, the array from 1 to 3, you actually, not knowingly, created a one-dimensional array whose tuple representation would be written like so. A tuple of one value 3. 3 representing the number of elements in your array. This one-dimensional array, this vector, is often used in mathematical operation. Typically in this course, we'll be dealing with higher dimensional arrays. How do we create a multi-dimensional array? Well, back to Jupyter Notebooks, recall that arrange is equivalent to Python's range function, but returns an array rather than a list. Let's make use of it again to create a 3x3 NumPy array by first importing NumPy as NP to access all the submodules and functions from NumPy through this alias NP. We'll make a variable x is equal to arrange np.arrange 3, which creates an array of 3 elements ranging from 0 to 2. Note that this is equivalent to writing 0 to 3, but by omitting the 0, it's assumed that you're specifying a start integer of 0 up until your stop integer of 3. Your array will therefore have 3 elements, ranging from 0 to 2, since the stop integer 3 is exclusive. Set y equal to the same thing, np.arrange 3, and do the same thing for z. All of these arrays are one-dimensional, each containing 1 row and 3 columns. However, if we were to combine them together, we'd get 3 rows and 3 columns, thus a 3x3 array. We can do that by declaring multi-array is equal to, we'll create our 2D array with the array function np.array. This function requires an object exposing the array interface. In essence, something that's array-like, whose method returns a sequence. A Python list will work just fine. We want our array to then combine all 3 arrays, x, y, and z. Based on what we passed into our array function, the output of this, what's returned, will be an array object that satisfies the specified requirements. Go ahead and print multi-array, and it outputs 3 rows of data. Each row has 3 columns. We can further show this by printing the shape of the array. Print multi-array dot shape, and it outputs a tuple indicating a 3x3 array, 3 rows and 3 columns. If I remove the x, we're then missing a row, thereby outputting a 2x3 array, such that we still have 3 columns. Alternatively, we could have created our one-dimensional arrays with np.linspace rather than arrange. This is similar to arrange in the sense that np.linspace, first let's write it down, it has a start and a stop index. They both have it. That is, if I specify a start index of 1 and a stop index of 10, it's going to grab numbers from 1 to 10, and the third number indicates the amount of samples that we want to generate between 1 and 10. Let's assume I want to grab 50 samples. If we print w, we get a one-dimensional array of numbers between 1 and 10. More specifically, it returns 50 numbers, and all numbers are evenly spaced. If we make this into 100, it gives back 100 numbers, all evenly spaced from 1 to 10. Do not confuse this with arrange's step integer. On a new cell, copy and paste what we have. I will call this b. b is equal to np.arrange. And if I indicate a step of 3 and have the numbers go from 1 to 30, the sequence is still going to be from 1 to 29, except that it would grab every third element in the sequence, whereas with linspace, this third argument specifies how many elements we want from 1 to 30. If we change it to linspace, it would grab 3 numbers from 1 to 30 that are all evenly spaced. So, take-home message, With arrange, this indicates step size, whereas with linspace, it refers to the amount of samples between your range. If I put this back to what it was, and remove the step size for now, just to make things more intuitive, notice how with arrange, the stop integer 30 is excluded from the sequence. It goes from 1 to 29, not from 1 to 30, whereas with linspace, it does include the integer at which we're stopping. It indeed goes from 1 to 10. It would still go from 1 to 30 if we specified it as such. Well, the thing with that is that linspace has a fourth argument. It's a bool value, which is by default true. If we set it to false, then it's not going to go all the way to 30. It is excluded. This was just to get you familiar with a function that creates 1D arrays aside from arrange, but now let's quickly move on to indexing. We'll go ahead and delete this cell, this one as well, and we'll go back to our previous train of thought. In the last video, we indexed a one-dimensional list using a single integer. The notation for indexing a one-dimensional array is the same, and it is also the same thing for a two-dimensional array, such that we can still write multi-array, and inside these brackets is where we're going to indicate the index that we want to access. Although, since this is a two-dimensional array, indexing is done with two integers, not just one. The first integer, we're going to call it n, indicates which row we want to access, and the second integer, m, indicates which column. We'll start by changing the range of our second array. It will go from 3 to a stop index of 6, so from 3 to 5, and also changing the range of our third array. It will go from a start integer of 6 to a stop integer of 9, so it's going to have a sequence going from 6, 7, 8. Accordingly, if we print out the multi-dimensional array, it seems that I forgot to put back my x. It would indeed output 0, 1, 2, 3, all the way to 8, each row containing 3 elements. Suppose I want to access the number 0. For our 3 by 3 array, rows are indexed from 0 to 2. 0 is located in the first row, which would correspond to row 0. Columns in this case are also indexed from 0 to 2, such that 0 is also in the first column, column 0. If we output this, we get back a value of 0. The value 5 is on the second row, third column. It is therefore on row 1, column 2. Output the value, and it results in a value of 5. Clearly, selecting elements from an array is very simple, and if you've done the Python crash course, you'll realize that it's very similar in how we index lists. Except now we have two integers, which represent the indices of the item in the array. If this array was 3-dimensional, at the moment it's 2-dimensional, as you can see by its shape. If it was 3-dimensional, you would require an extra integer. Finally, before we end this discussion, recall that NumPy arrays are generally homogeneous, such that items composing the array are generally, as you can see, all of the same type. We declared a homogeneous array. Therefore, the elements of that array can be described by the data type object, dtype. That is, by printing on a new cell, print multi-array.dtype, it outputs int 64, which indicates that all the elements of my array are 64-bit integers. Many functions like array, like arrange, have a data type argument, which allows you to specify the type of your output array. In our case, by default, a type int64 was inferred, 64-bit integers. We can specify the type of the output array to be something like int16. That is, dtype is equal to numpy.int16. If we run this cell, I forgot my comma, and run the subsequent cell, the element types are now of integer 16. It could even be an unsigned integer of uint8, for example. And now all element types are uint8. The point I want to make is that the Python integer and float type that we saw in the crash course, they are not enough for scientific computing, whereas NumPy has a lot more numerical data types than Python, whose precision depends on memory requirements. I've done it many times before. First, we'll import NumPy as NP, and then we'll set some variable x is equal to numpy.arrange 9. The array will have 9 elements that range from 0 to 8. And clearly, if we print this, print x, it prints a simple, boring, one-dimensional array. We can actually reshape this into a two-dimensional array. Reshaping does not change the data or alter the data in any way. Our array will still have 9 elements from 0 to 8, except now we'll reshape it to have 3 rows and 3 columns, all of which still contain the same data. You can do this by simply calling .reshape 3 and 3. Print the result, and clearly it's a 3 by 3 array, 3 rows and 3 columns containing our data. If I tried to make this into a 3 by 5 array, we'd get an error, which makes sense since a 3 by 5 array implies 15 elements. We only have 9. Remember, the new shape must define an array with the same total number of elements. Your dimensions must be compatible with the data. If I were to actually put -1, which denotes an unknown dimension, then the amount of columns in this case is determined such that the overall number of items in the reshaped array must work out to 9, given that we've already specified 3 rows. If we run this, it's going to work out to 3 columns, like we had it previously. We can actually take this one step further. Instead of just 9 elements, we can make this into 18 elements, and we'll reshape this array to be 2 by 3 by 3. Go ahead and print this. Clearly this array has 18 elements, 0 to 17, and we reshaped it to have 2 blocks of data, and each one has 9 elements shaped into 3 rows and 3 columns. In total, this corresponds to 18 elements. The best way to think about this is imagine an Excel spreadsheet with 2 sheets, and each sheet has 3 rows and 3 columns. Alternatively, we can reshape our one-dimensional array into a 3 by 3 by 2 array. Print the result, and we get 3 blocks of data, each one with 3 rows and 2 columns. The take-home message being is that reshape changes the shape of an array according to a tuple of integers. The new shape of that array, its new dimensions, must be compatible with the array's data. Otherwise, an exception is thrown, as we previously saw. Dimensional array with 3 rows and 3 columns. We've already covered indexing early on, but we'll go over it again very quickly, as it segues pretty well into our discussion on slicing. Suppose we wanted to access the number 7. The number 7 is on the 3rd row, 2nd column, and to access it, similar to how we accessed one-dimensional arrays, we'll use brackets to denote the indices. The 3rd row corresponds to index 2, and the 2nd column, index 1. Print out the result, and indeed we get our value. Imagine we had 18 elements, and we're now dealing with the 3 by 2 by 3 array, and we want to access the number 10. Imagine this was a building with 3 floors. The 2nd floor, where the number 10 is located, would have an index of 1. Now think of the elements as rooms arranged in columns and rows. Room number 10 is on the 2nd row, which would have an index of 1, and it's also on the 2nd column, which also corresponds to an index of 1. These indices therefore represent the position of element number 10, and indeed this is reflected when we run our code. So that's it for selecting a single cell from our array. What about segments, slices? This again is very similar to how we would slice a one-dimensional array. Suppose we want to slice the numbers 6 to 11. All of these are numbers on the second block of data, which has an index of 1. The numbers 6 to 11 are present in both the first and second row, therefore we would be slicing from the row indexed 0 to a stop index 2, meaning it would go from row 0 to row 1. So we're on the second block of data from row 0 to row 1. Now we just need to specify the range of columns. The numbers 6 to 11 are also present in all 3 columns. Therefore, we would be slicing from the column indexed 0 to a stop index 3, which corresponds to the columns indexed from 0 to 2. Running this gives us the numbers 6 to 11. Since we're accessing all the rows in this block of data, we can actually omit the range here, and it will be assumed that we're trying to access the numbers in both rows. The same concept applies to the columns as well. Since we're slicing all 3 columns, we can simply omit the range, and it will be inferred that we're trying to access everything from column 0 to column 3. One more thing to note is that since we're accessing the elements in all the rows and all the columns inside of floor 1, we can omit the stop integer, leave only the colons, and it will be assumed as such. And now, since we have multiple colons, we can use ellipses instead. That's another shortcut. This replaces both of our colons and clearly is still equivalent in its functionality as it produces the same output. What if it didn't matter what floor we got our data from, as long as our data is in the first row, first column? Once again, since we want data from every floor, you can either specify the entire range, which would be from 0 to a stop index of 3, therefore from 0 to 2, or you can simply omit the indices and it will be assumed as such. And now the first row in whichever block of data is denoted by the index 0, and the first column is also denoted by the index 0 regardless of which block we're in. Running this code outputs the result 0, 6, and 12. It doesn't matter which block of data our rows and columns are in, as long as it's the first row and first column, that data is displayed. To introduce the concept of step size, we'll revert this back to just displaying rows and columns on the second block of data. And we'll actually slice all the columns and all the rows with 2 colons instead of the ellipses. And now what we can do is we can also select each second element of our slice by indicating a step size of 2. And clearly it grabs every second element in each row. 6, 8, 9, and 11. Before we wrap up this lesson, we'll also introduce conditional selection with Booleans, meaning I can select elements from a list based on a comparison operation. First, we'll set a variable, comparison operation is equal to x is bigger than 5. We'll go ahead and print comparison operation. And what this will do is it creates a new array where each one of its elements is an evaluation of whether or not the elements of this array are greater than 5. Obviously, the elements that go from 0 to 5 are going to return false since they are not bigger than 5, whereas the rest of the elements evaluate true. We can use this comparison operation to return all of the elements of the array which are greater than 5 by simply placing it in the brackets as we did for slicing. X brackets comparison operation. And the output should return all the elements of the array were this expression evaluated to true, hence returning all elements greater than 5. We can go ahead and place the comparison operation directly inside of our brackets instead of declaring a new variable. it's still going to grab all of the elements in the array that are greater than 5. That is it for conditional selection. You will encounter it quite often in this course. We can also use the built-in max function to grab the highest number in the array. That is, I can write x.max, and similarly, we can use x.min to grab the lowest number. That is all we're going to cover for indexing and slicing. You'll see quite often in this course, so it's important that you get familiar with them now. The first function we'll look at is ravel, which flattens a multi-dimensional array and returns a one-dimensional array. Suppose I had an array with 9 elements from 0 to 8 that was reshaped into having 3 rows and 3 columns. We can flatten this array back into a single-dimensional array by calling raveled array is equal to the array itself x.ravel. Go ahead and print raveled array, and it flattens it into a one-dimensional array such that it now only has a single row. The flatten function does the same thing as ravel. We could try this out by setting flattened array is equal to the array itself dot flatten. Print flattened array. And indeed, it still outputs a one-dimensional array. The difference between the two cannot be distinguished with simply this print statement. But it's important to know that flatten always returns a copy and allocates new memory, whereas ravel would return a view of the original array. Why is this important? Well, if I were to modify an element in the array returned by ravel, it would modify the original array x as well. We could try this out by setting the element of the raveled array at index 2, we can set it to be 1,000,000. Print the raveled array, and indeed it is 1,000,000. But if we also print the original array x, clearly the change is reflected in both arrays. Whereas with flatten, since it returns a copy of the array, modifying the copy will not have an effect on the original array. For clarity, we'll revert our original array to have its initial value by rerunning all the cells and removing the code that we put. We will modify the flattened array to also have a value of 1,000,000 at index 2, 1,000,000. Do not put any spacing in between. There you go. If we print the original array, notice that it has no effect. Even though using ravel is much faster since no new memory is allocated, the side effect being that it's not as safe in the sense that one must stay mindful that any changes to the raveled array are also reflected in the original one. That is all for flattening and raveling. On another cell, we'll declare an array, a new array with 9 elements. Y is equal to np.arrange9. And now what we can actually do is, instead of using reshape to make this into a 3x3 array, as we did previously, we can set the array shape directly with y.shape is equal to a shape of 3 rows and 3 columns, and printing y results in an array of 3 rows and 3 columns as predicted. We can also flip a matrix over its diagonal, that is, obtain its transpose, by switching the row and column indices. You can do so by printing y.transpose, specifying an argument of none, and indeed it does flip the matrix over its diagonal as the rows and columns have been switched. An equivalent approach to this would be to use the t attribute, y.t, which has the same effect as the transpose function with no arguments given to it. We can also resize an array. Resizing not only reshapes an array, but it also modifies it such that if the new array that we're resizing it into is larger than the original array, then the new array is filled with repeated copies of the array that's being resized. Our original array is a 3 by 3. We can resize it into a 6 by 6. On a new cell, we'll print numpy.resize. We'll resize the y array, and it will have 6 rows and 6 columns. So specify a tuple of 6 rows and 6 columns. This outputs a 6 by 6 array, and notice how the data is repeated in order to fill in the extra 3 by 3 rows and columns that we added to it. Another useful function often used to create arrays is np.zeros. As the name suggests, returns a new array filled with zeros. The first argument is the shape of the array. We'll just have it be a one-dimensional array filled with 6 zeros. So we'll specify a tuple of only one dimension. Outputting this, notice how every 0 has a dot. The default type is a float 64. We can make the array elements into integer types by specifying a second argument, a data type, equal to integer. We will explicitly declare every single one of these elements as an integer type. Forgot the comma. There you go. You can go ahead and print this, and one thing to note is that another way to rewrite this tuple is to just omit the comma, and everything should still work out the same way. We can make this into a two-dimensional array of zeros by specifying a shape of 3 and 2, or 2 and 3, whichever one you want. A similar function to this is np.ones, which is essentially the same thing, except that instead of zeros, you'll get ones. Another useful function that's often used is np.i. We'll go ahead and print it, np.i. This creates a square matrix, meaning an equal amount of rows and columns, where all the diagonal elements are ones and other elements are zeros. This is very often used in linear algebraic operations. This will always return a two-dimensional array such that the argument is a number that specifies the columns and rows. If we specify 3, we'll get an identity matrix with 3 rows and 3 columns. Lastly, there are many ways to generate arrays with random numbers in NumPy. For example, we're able to create arrays of random numbers by calling np.random, and we'll use the rand function. This creates an array that can be one-dimensional or multi-dimensional and populates the array with random samples from a uniform distribution over 0 and 1. The only argument being the shape of the array. I want a 4 by 4 array. This results in 4 rows and 4 columns populated by random samples from a uniform distribution over 0 to 1. That wraps up this lesson. We learned how to further manipulate the shapes of an array with the resize method, as well as transpose, flatten, and the ravel functions. I'll cover it very briefly. Suppose we had a matrix A and a matrix B. Then the product of matrices A and B is defined only if the number of columns in matrix A equals the number of rows in matrix B, which is exactly the case, since matrix A has 3 columns and matrix B has 3 rows. And so, given that the condition is satisfied, the way this would occur is you multiply the numbers in the first row of matrix A with the numbers in the first column of matrix B. 0 times 3, 3 times 3, and 5 times 4, giving you 0, 9, and 20. Take their combination to obtain 29. We do the same thing, but now for the second column of matrix B, to obtain 0, -6, and -10, resulting in a value of -16 when taking our sum. Alright, now we're done with the first row. We do the same exact thing for the second row. But now restart at the first column of matrix B, 5 times 3 plus 5 times 3 plus 2 times 4, which equals 38. And now the second column, 5 times 4 plus 5 times -2 plus 2 times -2, which ends up equaling 6. And that is all. We've taken the product of 2 matrices, and let's do this in our code really quickly. First, we start by importing NumPy as NP, and then on a subsequent cell, we'll be defining a matrix. And defining a matrix is very similar to defining an array, where we set mat A for matrix A will equal numpy dot matrix, which will contain the same values of the matrix that we talked about earlier. 0, 3, 5, 5, 5, and 2. But we're going to reshape it to be a 2 by 3. Dot reshape 2 by 3, like what we had earlier. Outputting this matrix, matrix A. All right. And now on a different cell, we'll define another matrix. Matrix B, which we're going to set equal to numpy dot matrix. Again, the same values as before, 3, 4, 3, negative 2, 4, and negative 2. But this will be reshaped to have 3 rows and 2 columns. Reshape 3 and 2. And outputting this, matrix B, we get the following, just what we expect. And now multiplying matrix A times matrix B, conducting matrix multiplication, we obtain the result that we expected. The same output can be obtained by setting product is equal to mat mul, taking the matrix product of both matrix A and matrix B. And I forgot numpy.matmul. All right, and now simply outputting the value, we get the exact same result. Alternatively, we can perform the same operation on arrays by making both of these arrays numpy.array, numpy.array, and rerunning all the cells, we get the same result. There are many ways to perform this operation. Another option for arrays is to specify matrix A at matrix B. Once again, outputting the same results. That is it for matrix multiplication and how it can be emulated in NumPy, that are often used to manipulate arrays. We'll begin this lesson by learning how to horizontally stack 2 arrays. We'll begin using the hstack function, which stacks arrays in a horizontal, column-wise sequence. We'll start off by importing numpy as np, set x, sum array x equal to np.arrange 4. We'll have 4 elements from 0 to 3, reshaped.reshape 2 and 2 into 2 rows and 2 columns. Printing x, we get a 2 by 2 array. On a different cell, we'll make another 2 by 2 array, set y is equal to np.arrange 4, 8. We'll have 4 elements from 4 to 7, also reshaped into 2 by 2 rows and columns. Print y. And now, with the hstack function, we can horizontally stack these 2 arrays. Set z is equal to hstack. The parameter consists of a tuple of arrays. The arrays will be x and y, and don't forget to use the np alias before calling hstack to access the function itself. Note that for this to work, the arrays must have the same shape along all but the second axis. Outputting z, printing it, displays the 2 arrays stacked along one another. The arrays being stacked horizontally must have the same shape as we previously said along all but the second axis, which runs horizontally across the columns. The first axis, which must be the same, runs vertically downwards across the rows. They must match for both arrays. One thing to note about horizontal stacking is that it concatenates along the second dimension. If you print the shape of the initial array, we'll print x.shape. The output is 2, 2. Although printing the shape of the stacked array, print z.shape, will output 2 and 4. Clearly, concatenation occurred along the second dimension, increasing the number of columns. If I change one of my rows to be 1 and the number of columns to be 4, this would still work. However, an exception should be thrown here since they do not have the same shape along the first axis. Recall that for horizontal stacking along the first axis, the shape must be the same. Suppose instead we had an array with 8 elements ranging from 0 to 7, which can be reshaped as a 2x4. We would still be able to horizontally stack x and y, since they have the same shape along the first axis, as you can see. Whereas if I change this to a 4x2, the dimensions will not be compatible. However, if we were to vertically stack these two arrays and stack them along the first axis, it would work just fine. When vertically stacking, unlike horizontal stacking, the arrays must have the same shape along all but the first axis. X and Y have the same shape along the second axis, which runs horizontally across the columns. Therefore, we'll vertically stack them along the first axis with np.vstack. This also takes in a tuple of x and y, print the result, and it stacks them vertically. One thing to note about vertical stacking is that unlike horizontal stacking, it concatenates along the first dimension. If you print the shape of the initial array, as we did previously, the output is 2 and 2, although printing the shape of the stacked array will output 6 and 2. Clearly, concatenation occurred along the first dimension this time, increasing the number of rows. The equivalent to stacking is concatenating. We can achieve the same results as stacking by concatenating two arrays and specifying the axis along which we want to concatenate them. Recall that vertical stacking joins the two arrays along the first axis. The first axis is denoted by the index 0. So what we'll do is we'll np.concatenate. Again, this takes in a tuple of arrays, x and y, and we'll concatenate them along the first axis. Axis is equal to 0. If we set this equal to a variable w and print w, clearly concatenation along axis is equal to 0 has the same effect as vertical stacking. If we wanted to achieve the same result as horizontal stacking, recall that horizontal stacking occurs along the second axis, which is denoted by index 1. If you try to run this, an exception is thrown since they do not have the same shape along the first axis as would be needed for horizontal stacking. We can fix this by changing this back to a 2x4, and concatenation should work just fine. To show that horizontal stacking and concatenation along the second axis are the same, we'll also horizontally stack these two arrays. We'll set z is equal to, we'll reuse z, we'll set that equal to np.hstack x and y. What we can do now is we can use the comparison operator equal to check if both of these arrays are equal. So we'll do z is equal to w, and we'll print the result of that. What we get is it returns an array that displays true for every element, indicating that these two arrays, z and w, are identical for all elements. Therefore, concatenation along axis is equal to 1, and horizontal stacking are indeed equivalent. This also introduces the concept of comparing two arrays with the equal comparison operator. The same concept would apply to vertical stacking if you were to concatenate along the first axis, but we're not going to do that since that would throw an error. That is all for horizontal and vertical stacking. Next, we'll cover depth stacking. Depth stacking is not as intuitive as horizontal or vertical stacking, which stacks along the third axis, the depth axis. Before proceeding with depth stacking, let's ensure that both arrays have equivalent rows and columns, we'll therefore just set y is equal to x times 2, multiplying all of its elements by 2. Both arrays now have 2 rows and 2 columns. We'll declare depth stack is equal to numpy dot dstack, which takes in a tuple of arrays, x and y. Since both of these arrays are two-dimensional, and due to the fact that depth stacking stacks along the third dimension, which we don't have, what it will do is it will first reshape both of these arrays by inserting a third dimension of size 1. If we go back to our building analogy, both arrays would now have 2 floors, each floor with 2 rooms, organized in 2 rows and 1 column. If we print depth stack, since we added a third dimension to our array, stacking occurs along the third dimension, such that the third dimension previously added now contains 2 columns per floor. We can show this by printing depth stack dot shape, which results in a shape of 2 floors, 2 rows, and 2 columns. Main thing to note is that dstack adds an extra dimension 1 for both arrays. Unlike vertical and horizontal stacking, it concatenates along the third dimension, increasing the number of columns from 1 to 2. To show that the dstack function adds an extra dimension, we can explicitly declare that dimension ourselves for both x and y. Both of these will now have a shape of 2, 2, and 1. Depth-wise stacking would then occur along the third axis, joining both array columns and resulting in a shape of 2 floors, 2 rows, and 2 columns. Similar result to what we encountered previously. Do note that both arrays here have a third dimension of 1, and our array here has a third dimension of 2. So clearly depth stacking occurs along the third dimension, increasing our number of columns by 1 per floor. Next comes column stacking. This is another case where the name gives away the functionality. We'll revert these back to being 2 by 2 arrays. We will get rid of the third dimension. And what column stacking will do is it will simply stack both of these arrays along the second axis, which runs horizontally along the columns. In this case, it is equivalent to horizontal stacking along the columns. So we'll call np.columnStack, also taking in a tuple of arrays x and y, and by outputting the result, print, it horizontally stacks both of them in a column-wise direction. We can actually check if this is equivalent to horizontal stacking with the comparison operator, and we will compare it to a horizontal stack, np.hstack, taking in a tuple of x and y. The result is an array that returns true for every comparison between each respective element that composes both the horizontal and column-wise stack arrays. Column stacking and horizontal stacking differ when dealing with one-dimensional arrays. If we revert x and y to be one-dimensional by taking off the reshaping, with horizontal stacking, if I were to just print this on a separate cell and get rid of this, print hstack, horizontal stacking for a one-dimensional array, it would line both arrays up along the second axis, whereas column stacking would still stack them up as columns to make a two-dimensional array. In this case, the resulting output with 1D arrays from these two functions is not equivalent. The same concept applies to row stacking. The name speaks for itself. We will revert these back to being 2 by 2 arrays, putting back the reshaping. What row stacking will do is simply stack both of these arrays along the first axis, which runs vertically along the row. In this case, it is equivalent to vertical stacking. We'll call np.rowStack, also taking in a tuple of arrays, x and y. And if we print the result, it vertically stacks both of them in a row-wise direction. We can also check if this is equivalent to vertical stacking with the comparison operator. Set it equal, and we'll compare it to a vertical stack, vstack, taking in a tuple of x and y. The result is an array that returns true for every comparison between each respective element that composes both the vertical and the row-directed stack.